Hi there, my name's Andy. I'm a professor at UNSW in Sydney, currently working from home during the pandemic. I work on isotopes and try and use them to understand environmental changes in the past and what might happen in the future. I've got a few slides that might be useful for your HSC, so here goes. Okay, so that's what I do. That machine looks quite exciting, but actually that's been sped up at 10 times faster than usual, and it takes days to make all those analyses. I'm only joined by a team of researchers from around the world, and this is a photo of my group from a few years ago, working in Wellington Caves in central west New South Wales. We have colleagues here from Europe, Iran, and also from across Australia. And we're trying to work out how isotopes can tell us how quickly water gets into the groundwater system. That's just one application of why we might want to use isotopes in the environment. So I guess the question is, what are isotopes? So the example of an isotope that I'm going to use is the water isotope. And water is H2O, so 2 hydrogens and 1 oxygen. And you can see on this slide that that's written down as a chemical formula. So we have H2O16 on the left, H2O17 in the middle, and H2O18 on the right. And the 16 and the 17 and the 18 tell you that there's different masses of oxygen, and that's because there's a different number of neutrons in each of the oxygen molecules. Highest mass on the right, lowest mass on the left. Each one of these different oxygens is a different isotope. They have slightly different masses, and because they have slightly different masses, they behave slightly differently in the environment. And that's the property that we use when we're trying to understand past environmental and past climate changes. The numbers at the bottom are the relative abundances of these different isotopes. So it's out of 10,000 water molecules. So if you've got a drinking water bottle in front of you, or you can imagine a glass or a cup of water, and there's going to be many, many molecules of water in that glass or that container, for every 10,000, 9,977 will be the lightest molecule, H216O, and only 20 out of that 10,000 will be the heaviest molecule. And that's a common property for almost all isotopes in the environment. The lighter isotopes are the most abundant, and the heavier isotopes are the least abundant. The practical implication is that we need to have a very sensitive analytical instrument to be able to measure just 20 out of 10,000 of the heavier isotopes if we're going to reconstruct our past environmental changes. And I'll come to that in a minute. So let's look at hydrogen. Hydrogen has 3 isotopes, 2 of which are stable, they don't change over time, and 1 of which is radioactive. The 2 stable isotopes are a hydrogen with a mass of 1 and hydrogen with a mass of 2. So the hydrogen with a mass of 1 has 1 proton, 1 electron. Hydrogen with a mass of 2 has a proton, an electron, and a neutron. And the same as oxygen, the lighter the isotope, the more abundant it is. So in this case, hydrogen with a mass of 1 is 99.985% of all hydrogen. So just 15 out of your 10,000 will be present as the heavier isotope, or 2H. 2H is also sometimes written down as deuterium, and it's sometimes used as the symbol D. So if you see that, don't be confused. The third isotope, which I won't talk about anymore, is used in dating. It's radioactive, it has a half-life of about 12 years, and that's hydrogen with a mass of 3. And because it's got a mass of 3, it's also called tritium, and you might see the word tritium when you do some reading. But I'm not going to talk about that anymore for the moment. Okay, so why do we bother with isotopes? So here's an example from an ice core. It's from Greenland, and a team of scientists have drilled a core down through hundreds of meters down to the base of the ice to try and work out the record of past climates. As you go deeper and deeper into the ice, you have a record of the snow that accumulated in the past. And that snow is frozen water, and it comprises of the water isotopes. So if we can measure these water isotopes and we can go and drill back into the past, can we say something about past climates and past climate change? That's the question on the syllabus. So to be able to understand some of these figures, what you need to understand something about is, what does all this mean here? It says something that says there's a delta symbol, this big thing here. Then there's the 18 oxygen isotope, and then there's this symbol here. So what do they mean? We need to explain those for you so that you can then look at these graphs and understand what do these values mean, going up between minus 33 and minus 45, and why does that equate to a temperature change of 11 degrees centigrade. So what are these delta and this other symbol, which is called per mil? What are these things? And if you read textbooks and look at figures and graphs, you will see isotope values reported something like the two examples I've got on screen here. You might see delta 2H equals a value which is positive or negative with the per mil symbol, and then a bunch of letters afterwards which don't mean anything to you at the moment. In this case, we have VSMO2, and underneath that we have PDB. What do all these things mean? So first of all, the delta 2H in isotope terminology means it's a ratio of the two different isotopes, hydrogen 1 and hydrogen 2, and it's relative to a standard. And as we'll find out in a minute, the standard is this long set of letters or letters and numbers that follow the values. Because we know that the relative abundance of the two isotopes is such that there's a lot of the lighter isotope and very little of the heavier isotope, if we take a ratio of the two abundances, we'll have a very small number. So just for convenience, these ratios are multiplied by 1000. And the symbol to show people that you've multiplied the values by 1000 is the per mil symbol. So it's a bit like a percent symbol, which tells you you've done something by 100, and there's an extra 0 at the bottom to say it's by 1000. And if you ever need to type that, this is the control code that you need in Windows. Okay, so far we know that we have a delta symbol, and that tells us that we're going to ratio the two isotopes, the heavier and the lighter, and it's relative to a standard. And the standard will vary depending on what you're measuring. So for water, the standard for water isotope measurements is this thing called VSMOW2, which stands for Vienna Mean Standard Ocean Water 2. And it is just a large sample of ocean water that was collected by the scientific community and then measured in great detail to work out the isotopic composition for the water molecule. And then it was packaged up and sent around the world to all the laboratories around the world so that everyone had a common standard value. And the value that's been given, by definition, is 0 per mil. So when you see that a water isotope value has a value which is in a delta notation and with a per mil symbol at the end, and it says it's VSMO or VSMO2, you know it's relative to the standard, which is ocean water. So isotope compositions may therefore be negative or positive compared to the standard. And a negative value means there's less of the heavier isotope compared to the standard. And a positive value means there's more of the heavier isotope compared to the standard. So why do we do this? Well, we do this because the stable isotopes change with different environmental processes. They can tell us about what happened in the past. And those processes can be physical, they could be chemical, or they could be biological. And the term is often used in the literature is called fractionation. So the fractionation of the isotopes, the changes between more or less of the heavier isotope, can depend on things such as temperature, and therefore it can tell us about climate and past climates. So if you're happy with how the isotopes work, what they are, what the per mil symbol means, what the delta symbol means, then you can go off and start looking at the examples of how scientists have used this in the past to try and work out past climate changes and current environmental processes.